Code seems like it's everywhere these days. It is used to run the obvious things such as video games, computers, tablets, and machines, but it's even used to run some things you wouldn't think use code, such as showers, cars, traffic lights, elevators, and even agriculture. Code wouldn't be possible if it weren't for the foundation base of it all, binary. A German man born in 1646 by the name of Gottfried Leibniz was the mathematician who invented binary, the base of all code and programming today. Leibniz was a renowned philosopher as well as a mathematician and was even believed to have invented calculus, though there are many arguments that Newton invented it first. Binary was first used in the coding aspect in 1938 when the Zeus Z1, built by Konrad Zuse, was completed. It was the world's first freely programmable computer and was used as a binary calculator.
Binary may seem to be a very complex and confusing subject, but if you break it down, it really is very simple. An easy way to look at binary is this way. Back in first grade, you learned about place value. There's the ones place, the tens place, the hundreds place, and so on. When you write a number, you really only use the digits 0 through 9. If you write a digit in the ones place, it's multiplied by 1. When you write a digit in the tens place, that number is multiplied by 10. When you write a digit in the hundreds place, that number is multiplied by 100, and so on. Binary is just as simple. Base 10, which is normal numbers, uses a base of 10 numbers 0 through 9. Base 2, binary, uses a base of 2 numbers, which are 0 and 1. In binary, the ones place is still the ones place. If you write a 1 in the ones place, it is equal to 1. Simple. In binary, each place is double the last value, instead of each place being 10 times the last place's value. The tens place is replaced by the twos place because that is double 1. If you write a 1 in the twos place, it has a value of 2. The next place would be the fours place. That's double 2. Write a 1 in the fours place to represent 4. Are you starting to get it now? If not, don't worry. This next demonstration should clear things up a little bit. Let's have some practice. Here's a place value table for binary. There's the ones place, twos place, fours place, eights place, etc. If we wanted to turn a binary number into a normal number, all we would need is this place value table and a piece of scratch paper. Let's try the binary number 111101, which is my personal favorite. No, it isn't 1,111,101. It is a completely different number. First off, here's how you pronounce a binary number. It's simple. Just start at the left and read off the numbers left to right. No place value knowledge needed. You would read it 111101. Okay, now let's convert it. We can start on any digit, but to make it simpler, I'm going to start in the ones place. As you can see, the 1 is placed in the ones place and has a value of 1. That's pretty straightforward. The next one, which happens to be in the fours place, has a value of 4. If we add the numbers 4 and 1, we get 5. 101 in binary is 5. Let's continue. If we have all the numbers the ones are representing, we will end up adding the numbers 64, 32, 16, 8, 4, and 1. We don't add a 2 because there is a 0 in that place. After adding up those numbers, we end up with a grand total of 125. See? It's pretty simple. Now let's try converting a base 10 number into binary. I'll pick the number 60 because it isn't too hard and can be converted fairly quickly. To start, you would look at the place value chart and find the largest number that can go into 60. In this case is 32. We would place a 1 in the 32's place and subtract that from 60. Since there's a 1 in the 32's place, now we are left with 28 instead of 60. 16 goes into 28. It happens to be the next largest number that works. We would place a 1 in the 16's place and subtract 16 from 28. We're now left with 12 instead of 60. The next biggest number that goes into 12 is 8, which happens to be the next number divisible. After we place the 1 in the 8's place and subtract 8 from 12, we are left with 4, which goes perfectly into the 4's place. We add zeros to the rest of the places, and now we figured out the binary equivalent 60, which happens to be 111100. Does that clear things up a bit? If not, leave a comment below and I'll be sure to help out further. You may think that chaos ends with numbers being converted to binary, but believe it or not, letters can be converted to binary along with numbers. Every character in the English language has what is known as an ASCII code. The ASCII code for capital A, for example, happens to be the number 65. If you convert the ASCII code to binary, you get the binary counterpart of that letter. The binary version of capital A is 01000001. Here's the list of ASCII codes for every lowercase and uppercase letter. Thanks for watching. I hope you understand binary a bit more now. This video is part of a passion project that I'm going to do for English. I'm going to be learning 6 new coding languages in the next 6 weeks and making YouTube tutorials for them to help others understand binary a bit more. Next week I'll be learning Python and creating a tutorial on it. Hope you're excited. Bye!